This is kind of the summary of, there was the beginning and it's kind of the end of last class. It was a bit of a pretentious already. What did I write wrong? No. They cut it already. Yeah. Yeah, it's true. It's true. I'm going to comment on it in a second. It's like spot the difference. There is one difference between last class and today, which is here there is y instead of r, or there is r instead of y. I'm going to comment on it in a minute. It's kind of an annoying bit that I never know which way is better, and we'll discuss it now that we know why it's worth discussing it. Anyway, so this was the beginning, and it's kind of the end of last class. What we did is kind of a explosion of every symbol into some meaning, okay? Discussing at length what are different input space, output space, why probability distribution, why taking this decision theoretic point of view where you don't consider the problem of estimating a probability distribution, but only a function, and then the necessity of introducing a measure of errors and defining the problem, okay? The problem of finding a function which is good on future data, a concept captured by the idea that we want to ideally be able to make the expectation with respect to the true underlying distribution small. And then the crucial point for that make right the use of the word learning, which is the fact that we don't have actually access to the distribution, but only to a bunch of points. Okay. This is roughly what we discussed last time. Again, we assume basically that we do have knowledge of what these are, the input space is, but rho is not known. L, on the other end, is known. We made a few examples, and we tried to get a grasp of what was the meaning of the loss function and how we could compare different loss functions. As your colleague immediately noticed, last time I introduced here y from y to, the loss function was from y times y into 0, 1, okay? Now, typically it's not, okay? So it depends a bit on the story. So typically, most of the situation you have that, the prototype example is, say, in regression, what you have is that typically you take real valued function, and you might have that the data are also real valued, but maybe not the whole real line, some subset. So y is just a subset, okay? Then you have binary classification. Binary classification is the case where this is plus or minus 1, and this we have to decide, okay? Because if you want to just take a decision theoretic point of view, you can say, I'm looking for Boolean functions. And then you basically can consider some loss function that just take an input to just two values, okay? 0, 1 here and 0, 1 here. But most functions used in practice actually don't do that. They have this kind of disparity between the first entry and the second entry. So in the first entry is just, say, plus minus 1 or 0, 1, but the second entry is actually just a real number. If you go to more exotic situations, say, for example, multi-class classification or something else, as we discussed, this is kind of a different, complicated business because the design of loss function, not for regression or classification, is actually a topic of research and is not something where we have clear ideas. Oftentimes, it still happens that you have to put into the game two spaces. The output space, which is structured, lacking linear structure, for example, and then some other nicer space that you use to estimate functions, okay? Later on in the course, we'll make some example. This class, I actually decided to go for this because from now on, we're going to do this, okay? Either it's going to be a regression problem or a classification problem where anyway, we decide to just look for real valued functions. So from now on, I'm going to use, well, in fact, I'm not sure I'm going to repeat this one line many more times, but we go for this kind of definition, okay? It doesn't really change anything substantial. One bit of information I gave you last time is that you can get a grasp of what is the difference between the different loss function by essentially massaging this a little bit and get an idea of what you can say about the actual minimizer, what we call the target function. The target function would be the solution of this problem, where this calligraphic F means all the possible function where this expectation is well defined. Clearly, neither the knowledge of rho or being able to handle the largest space of all possible function is anything practical, but still it makes sense from a theoretical point of view to try to derive an analytic expression, to just look at it and see what it is. And we did this by basically introducing one trick, which is described in detail in the, I'm not sure in detail, it's described in the notes, and it's part of the P sets, so you're gonna meet this idea again. And the idea was basically to first just use the fact that we assume always that this distribution can be decomposed in the marginal and the conditional, and then basically reduce the problem of computing the minimum, which is a function, to actually find the function at every possible point. We fix one point, but it's any point, and so it basically the basic idea was to consider what we call the inner risk that makes the problem of finding a specific function turns it into the problem of function of f at any point. And the idea is that this becomes a real number, and so the problem becomes easier. And somebody like to call this y prime, so I'm going to call it y prime. Okay? We're not going to repeat this. It is just is actually a trick to do a computation, an analytic computation, and it sits on. It's possible because of some fundamental result that we also don't want to do. That's not the interesting part of the discussion. Part of the discussion is what you get out of doing that trick and using that trick. And if you remember, we came to realize that by choosing the loss function, you're actually changing the target of the learning problem. If you consider the square loss, we saw that the target function is just the average of the y's for every point. Absolute value, the median, and keep on going. Clearly, in the regression, this means that we're actually changing the target. Okay, we literally consider different functions. For classification, what you see is that the story is slightly different. And long story short, we'll see that these are different flavors of doing the same thing, which is shooting for a loss function, which is convex, and yet find a decent approximation of the Bayes rule, which is just the one that says if you're doing classification, look at the conditional probability, P of 1 given x and P of minus 1 given x, and go for whatever label has higher probability. If P of 1 given x is bigger than P of minus 1 given x, go for that. Okay? We'll see that the square laws, and we're going to check the logistic loss or the hinge loss do exactly that. They provide a loss function that is able to mimic to some extent the decision rule provide or derive a target function that mimics to some extent the Bayes decision. Okay? Again, we don't want to discuss it too much here because this is going to be something that you're going to bang your head a bit on more during the problem sets. But it's a first insight on what is the role of loss functions, okay, and how you choose them. We'll see that another one is going to be the different loss function entail different form of computations, different kind of computation to actually find an estimator. And so that's what we want to start to discuss now. How the hell you solve this problem? What are the rules of the game? It's actually going to take us a few more classes to define algorithms. Today we want to begin very briefly, just deciding on what do we mean by solving this problem. It's worth a discussion because we're basically asking ourselves to solve a problem for which we have very little access to. We don't have access to any of this. We just have access to the data. So the hope to give a precise, exact solution to this problem is very little. It's almost. So that's what we want to ask ourselves. In which sense can we hope to solve this problem? What would be a good solution or a bad solution? An exact solution is out of the game. Before we do that, let me also just add one little remark. It is something that I never thought about, but I heard it recently, and it turns out that it happens all the time. I have mostly in my mind the situation where rho is fixed but unknown, and this is the classical situation for learning, say, and solve perception problems like vision, speech, or many others. In many branches of applied sciences, when machine learning is used, it's not because you have access to this. You actually have access to this. Say, physics is one example, or geophysics is another example. You actually know this process. But if you actually were to try to sample it in order to solve this, it would take forever. So what you do is that you actually take a bunch of subsamples and try just to find the function that you can compute quickly, okay? As opposed to do a crazy, ginormous simulation every time you have to make a decision. So again, this is just an entry point for a discussion. There are situations where you might actually have access to distribution, but it might be very costly to sample it all the time. So you just try to sample it n times and just get a good proxy. in high energy physics, for example, that's kind of the situation they have. They do know the standard model that gives rise to the phenomenon, but they actually try to still reduce it by synthesizing it through a function that you learn from samples. End of the remark. So what do we mean by solving this problem? And what do we mean by a solution? Well, generally, we can very broadly speaking, we are interested into maps from the data to some function, some estimates. Again, when you see a hat or n, it's typically some estimate from the data. S here is just a sample, what we call sometimes the training set. We're interested in some map like that. Some terminology. Typically, we call the map from the data the learning algorithm. And we call its output an estimator. Potential solution to learning problems, sometimes called an estimator. One thing I would like to start to commemorate is the idea that the term learning algorithm is sometimes, might raise some confusion because it has two different aspects, a statistical aspect and a computational aspect. So we actually be worried about both. But we'll see that there are situations where one defines a procedure that makes sense statistically, but doesn't entail specific computation. So then you still have to worry about computation separately. I imagine many of you are familiar, for example, with supervector machines or logistic regression. Is logistic regression an algorithm? Depends who you ask. If you ask to a statistician, he would answer probably yes. If you ask to an optimization person, we would say no, it's a problem. It's not an algorithm. Because logistic regression gives rise to actually something that you have to still to solve. Okay? So this is something that we want to start to think about. When we talk about learning algorithms, sometimes they're actually computational procedures. Other times are just some statistical procedures. They might be confused for now, but you'll see this making sense for sure in one class or two. That's what we want to start thinking about. How do we build something like that? Something go from the data to some actually proxy of the solution. Well, one first idea is, suppose that you do have something like this, because the first thing you want to do is, what is a good algorithm or a bad algorithm? A good algorithm should be something that provides a good proxy to the solution of this problem. So how do we write it down in one equation? What would be a good f or a bad f? An f that I find from data, an f hat, is good if the what? So you're basically saying I take the loss on the data. Let's give it a name. Let's call it the empirical error, empirical loss. And then I say I'm happy if this number for the specific guess I'm making is close to what? This? That's what you have in mind? So if this is close to the minimum, okay? That's one possible requirement, is the deviation between empirical mean, something you can compute on the data, and the actual problem, okay? And sometimes the deviation of these two quantities is related to what one might call the generalization error. And it's a pretty common quantity that appears in some form of, in some fields of optimization where people study convergence of functionals, empirical functional, epiconvergence, and so on and so forth, for those of you who know what this is. Fair enough, that's a good guess. Can you see another? This is the problem, and I would like to find a solution, an approximate solution. Right, why, in some sense, I think that from a mathematical perspective seems to be the more natural thing to do. I want to get something with this, I want to minimize this objective function. Give me something that, let me check how big is this objective function, right? So I would like to minimize this, but I cannot. Well, I still would like to find a function for which this is small. That's what you just said. Okay, there is the he, at. It might be confusing the first time you see it, but the point is that this is just an empirical quantity you can compute, fine. But from a just theoretical perspective, you want to make this small. Well, check how big it is for what you found. Of course, you cannot do it in practice, but here we're just defining what is a good solution from a theoretical point of view. And this seems to be the natural to look at. In fact, this is just the natural metric in which we measure success whenever you minimize a function. You find an approximate solution, and then you check how far is the value of the function from the optimal one. Okay? If you ever see any proof in optimization, that's what you do. And if you want, this is nothing but what people in optimization call a stochastic optimization. This quantity here is what is called excess error and excess risk, and we're almost done introducing the quantity. We still have to worry about something. For example, this thing depends on the data, and I could ask, for example, if this thing goes to 0 as the number of points goes to infinity. But how can I make it precise? Can I just write a limit here and say that this goes to 0? No, otherwise we wouldn't be asking the question. But why cannot do it? Why can't you do it? Because f is random, and so I have to worry what does it mean that this quantity goes to that or that the difference goes to 0. I have to do something like that. We have to decide. So she's saying I have to require convergence in probability. Well, I mean, somebody else may say in expectation, but certainly we have to worry about something. This is a random variable. So if you want to say that this goes to 0, we have to agree on how it does it. Okay? And for example, one possibility is to say, let's study this, and let's study its behavior. Okay? But we need to do something like this because we are doing a random quantity. Notice that I don't put any absolute value because I know that this is the smallest of all possible values, so I don't have to put any absolute value here. And basically, this is the exact way in which we say that a solution is, from a point of view, is when we have a solution, we measure its quality, basically studying this kind of quantity. Learning theory, the theoretical part of learning that studies the statistical properties of procedure, is exactly about studying this quantity. And you typically have two kinds of notions, and we'll discuss this stuff basically when I'm gone, I mean, when the last point of my, in 15 classes. You can ask this quantity to go to 0, just convergence, and that's what is typically called consistency. Okay, it's just convergence. Then you can ask a more quantitative requirement, which is not only to know that it goes to 0, but to know how fast it goes to 0 with the number of samples. This would basically mean that we actually want to try to bound this quantity in an explicit way that depends on the number of points and the precision at which we want our solution. Okay? We want to know exactly how fast this goes to 0, and this is going to depend on how many points we have, for sure, and also on how much precision we want. If we want a very small precision, we probably will need more time. If we want a very bad precision, less. Okay? The two questions are not unrelated. One is basically convergence, one is convergence with rates. These kind of results are sometimes called the tail bounds, because this is like, if you can think of this as the tail of the distribution, but also as a finite sample bound, in the sense that provide a quantitative answer for any finite number of points rather than a purely asymptotic statement. Okay? Yeah.
Why don't you just
Why don't I do what? I mean, this is one possibility, okay? So another thing you can do is you could put an expectation, or you could put almost sure convergence. That's what you want, almost sure convergence for? What do you mean normal convergence? It's a random variable. For any point. Yeah, you can do something stronger than that. This is a very weak requirement. It implies by pretty much any other one you can list. Okay? So let's say one thing to note is that it's useful to look at this because the moment you actually get an explicit bound, this becomes a very strong result. It implies most of other kind of convergence and probability. So just to wrap up this question for everybody, he's asking, why do you just look at this quantity going to 0? You can look at the expectation, you can look at almost sure convergence, you can look at pointwise convergence. Yes, you could. And this is the weakest of them. I just really write this down because it turns out that if I actually can get rates for this kind of convergence, meaning that I can get something like this, I get a concentration result, I get a finite sample bound. This is actually a very strong result. And from this, if this delta is good enough, I can actually derive most convergence in probability that you want. Yes? When you say rate, for now, what I mean by rate is an explicit functional form here, okay? An explicit expression for this delta term. This delta term has to be maybe not monotonic, but a decreasing function of the number of data points for any epsilon, okay? That make sense? Yeah, but a random variable is a function from a probability space. Okay, so literally, the f hat is a function on a probability space. Yeah, the function. So f, this one. The point is that this is not a function. Is a this this guy? Yeah. This quantity is just a deterministic quantity. Exactly. You mean, why don't I just look at f hat going somewhere? Yeah, but my goal here is to say, so my goal is to quantify sense a map from the data into a function is good or not. The data are random, okay? The map itself is deterministic. It could be randomized, but it could be a randomized algorithm. We're assuming that we're dealing with deterministic algorithm just for the example. So the map from here to there, I assume it's deterministic. Still, because the input is this is the definition of a random variable, and then I have to worry about that. And so this is what we're doing now. Okay? Okay? All right, so we won't expand on this too much, okay? We have classes devoted exactly to this topic. For now, what we wanna think about, okay, if this is what you wanna do, then how can we start thinking about designing such a map? Okay, the job of learning theory is to prove that when you invent an algorithm or to provide indication of how to invent algorithm that actually allow to control these kind of quantities. Okay, and this is actually true for big chunks of statistics anyway. One question we want to start asking is, okay, how do you start designing learning algorithms? Okay, and the basic idea starts again from basically looking at this and think what you can do and see what you don't like about that. Well, you don't like at least two things. One is that you don't have access to the probability distribution. Two is that you don't have access to all possible functions in the universe. How can we start thinking about fixing these two problems? Rather than considering that problem, we could consider another problem. Which one? Again, you don't like the fact that you don't like the probability distribution. You don't know the probability distribution. And you don't like the fact that all functions in the universe are kind of a lot of functions. What can you do? Replace that problem with something else. What? Well, what is that you know? The data. So you could say, well, instead of this, let me consider E hat. Let me replace the true error with the empirical error. Okay? So I could start consider something like this. And what do I minimize? Well, again, if we want to do something that is useful in practice, we have to have access to the space of functions. And the space of all possible functions is too much. Okay? We need a parameterization. So the next idea is to try to replace all possible functions with some more manageable space, some space with some structure, okay? Which can be very large, but has to be more manageable, okay? So this is one possibility. Make sense? This is not the only way in which you can do things, but this is a good start, and it starts to, point us in the right direction. We'll see that this is what is called the empirical risk minimization principle. ERM. Empirical risk theory, sometimes called the risk minimization. And it's kind of one of the main principles, okay? And if you start to go this way, the thing you have to worry immediately is, okay, I can see how I can do this, but these I have a lot of freedom. How do I replace the true space with another space? And you can immediately see that there is something going on here. Because basically, you can imagine that differentiation happens if h is big or if h is small, okay? So what do I mean by h being big or small? Well, okay, I have the space of all possible functions, and say I can take the space of functions. Okay, that's presumably a much smaller space than the space of all possible functions, as it is the space of polynomial of degree 2 or degree 3. Okay, or I can take, say, a large space, the space of all possible polynomials of any possible degree, plus the Fourier series and plus a bunch of other functions made of Gaussians or whatnot. Okay, that's clearly space, and that's kind of the distinction I'm making here, okay? Well, what you might expect to be the benefit of picking H big? If you pick a large space, then what might happen? Right, so she's saying I have a big H, I have a lot of options, so I'm most likely to be able to find a function that is the right one, okay? How do we formalize this in a symbol? Well, consider the situation where you're lucky to have a ton of points. You really have a lot of points, okay? You're so lucky to actually give you infinitely many points. Then this guy just becomes the true risk. But I'm still replacing the true space with another one, okay? So even if you're so lucky to have a lot of points, let me just use a shorthand notation. You will be considered this minimization, the minimization of the true risk over my space H. I just delete F from the business because I'm going to write this 4 times now. If H is big, what she's saying is that I can actually get close to the true problem, which is that guy, okay? So this is nice. I take a big space and I'm not changing things too much. What's bad? Well, in practice, you don't have access to this, okay? So this is just a toy picture, but you don't have access to this. What you have access to is just the empirical version. The problem is that if you have access just to finitely many data and you allow yourself a big space, you can explain anything you want. I never remember, this Feynman or Wiener, you give me 3 parameters and I fit everything, give me 4 and blah, 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 blah. It's actually a good one. Tommy, do you remember this? How many parameters do you need to do what? Who said that? All of them all together?
Sorry?
No?
That's the quote.
Anyway, so the point is that this is kind of the same story here. I give you this ginormous space, and then I can pretty much do everything. Particularly, I can drive to be very small, right? I can just make the error of my data very small. And yet, this can be whatever it is, okay? So typically, I may have a situation where this is small, but if I actually look at the true value, I get something much bigger. And it's not like I'm getting anything useful out of this picture, okay? So that's one extreme. Then you have the other extreme. If you take H to be very small, kind of these two things just get reversed, okay? If I take H to be very small, there is not much space to look for functions, okay? And so I'm likely to find something on finite data that is the same I would find if you give me a lot of data. Sorry, this is what I want to write. Okay? So I'm happy because my minimum of H is roughly the same, but I have that what I do on data is much different, okay? If you take large H small, you got the other way around, okay? Likely these two problems are going to be very similar because, you have very few functions to look into, the opposite of what I was saying a minute ago. On the other hand, your right function might not be there. And if it's not there, you don't find it. So the moment you have to start to thinking about this space, this what is called the hypothesis space, the space where you pick an hypothesis, you have to worry about how big or small it has to be. And that's where the keyword that we're going to use 50 billion times in this course enters the picture. The idea of regularization, the way we're going to use it, is oftentimes the following. We're going to try to build relatively large hypothesis spaces, and then we're going to try to explore them. So pick H large, and then regularization abstractly would be a procedure to explore H controlling the complexity of functions. Okay? So here complexity I put in quotes because it doesn't mean anything, right? It's just an intuitive notion. I have a big thing, which again I just qualify very roughly, and now I'm going to explore it by being able to say what's living in smaller space and will live in larger space, what is simple and what's complicated, okay? So that's basically what we're going to do for the next two classes, for today and next class. We're going to introduce function spaces and get a feeling what does it mean to have large function spaces, small function spaces, and a way to explore them. And we're going to explore them typically by introducing norms. We're going to say we're going to introduce norms, functionals that attach to each function a number. If the number is big, that thing is complicated. If the number is small, that thing is simple. And I'm going to try to make sense of how this can be done. It will not just be one way, but many ways. Okay? This is going to be our strategy. Once we've done this, we'll be able to design learning algorithms. Okay? And I would say the majority, at some level or another, this is the way the majority of learning algorithms develop. You fix some potentially large function class, and then you find a way to explore this function class. Okay? Again, this is a bit abstract because we're going to have essentially, at this point, 13 and a half classes to give examples. Any questions? Functions. Clearly, it's a I wrote functions. Yeah. I'm evaluating them efficiently. I try to use words so that I state when I'm too sloppy. Evaluate efficiently. I'm just saying I want to be able to explore them in such a way that I can, know when I'm looking at a complicated function or a simple function. Okay. So we're talking about large spaces and smaller spaces. You basically have a way to explore in such a way that you know within a large space where you're considering smaller subsets or larger subsets in some sense. Okay. And give example in 1 minute. But that's the idea. Of course, let me give you an example. I take the space of all possible polynomials, and then I consider polynomial degree 2, then 3, then 4, then 6. Okay? Or I take functions that are harmonic function made of sine and cosine with many frequencies, and I take all of them. Okay? All the function up to a certain frequency, but function that are very smooth, they are very low frequency, then higher frequency, and higher frequencies. Okay? The bigger space I can get is what I call H, is large, and then I have strategy to actually parameterize or explore this function, the degree of the polynomial, the amount of frequency, and you can imagine we can keep on going for a while with this kind of example, but that's kind of what. And for now, we have not talked about computation. Then we have to worry about how you do it computationally. And this is going to become a twist in the whole story, okay? What we want to do today is actually start to introduce function spaces and start to understand how we can describe how simple they are. And we actually start from the simplest function, the space of linear function, because it turns out that this is basically the paramount example on how we build function spaces. Using the same kind of ideas that are needed to build function spaces that are linear, we'll be able to build many, many other function spaces. So let me see if I'm forgetting something. What I would like to talk about today is exactly the main character of today's story is going to be H. And we want to discuss 4 things. Well, I guess it's going to be more 2 or 3. One is linear functions, or functions on finite dictionary. Then we would like to introduce the notion of reproducing kernel Hilbert spaces and reproducing kernel. And I'm not sure we'll manage, but I would like to touch upon the idea of positive definite kernel. Okay? Here we'll make a big example, which are translation invariant kernel. Let me say now, because it's a good point, because I'm not saying anything interesting. Well, a question that one might want to ask and get out of the business, why do we talk about reproducing kernel-based space if the only thing that exists is neural networks and kernel methods are dead? Okay, that's a legitimate question. And the answer is, well, because actually RKHS is not just kernel methods, they are function spaces, and it's actually very hard to meet a function space which is not a reproducing kernel Hilbert space. They appear everywhere. In signal processing, they're everywhere. In statistics, they're everywhere. In stochastic calculus, they're everywhere. They're called Cameron-Martin spaces in that case, and you can keep on going, okay? You will see in a minute, we take a path that shows that these things are not very specific. They're actually pretty general things. They just so happen that they're function space that just putting two properties, you get a bunch for free. Okay? And so in some way, it's kind of more of a foundational discussion where you just see an object that is going to be useful, even if you do other stuff. Whenever you study even function spaces that are given by neural networks, you typically try to get back to things like this because they have enough structures, okay, to study them. So that's why we do them. And also because they will allow us to introduce the classical method that we use for ages, like linear methods, generalized linear models, or models based on linear features, and non-parametric models, okay? And we're going to not discuss, we're going to touch upon Gaussian processes because we basically introduce the whole story of kernel methods in all its various forms. And so these are going to be our main one tool that we use for a bunch of lectures. The way we start the whole story is through linear functions and the dictionaries, because basically these introduce a lot of things that we like. So what do we like? We like spaces of function that are big but not too big, and that allow for control the complexity of a function in a sense that we have to make precise. But also, at some point, we stop pretend that we are just statistician, as I've been doing so far, just discussing minimum of that and another that. But somebody actually asks, how about computations? Yes, we have to worry about that too. We have to set up a space H that is something which is manageable in some precise sense. Okay, and that's what we want to do. So again, the first example you can think about is a space H, a function from X to R, such that there exists a W in RD, X is equal to W transpose X for all X in RD. Okay? And clearly here I'm making the assumption that my input space is RD. Okay? So already you can ask, okay, this is nice, but I would want to generalize this to a more general set. Graph, strings, probability, blah, 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 blah. For now, we stick to this, okay? Why do we love this space? Why is the fantastic space? It sucks because it's not very rich, but so why is it so nice? It's linear, and you get the whole thing for free. It's more than that. It's linear and finite dimensional. What we get is that we talk about function, but really we're dealing with vectors. It's indeed a linear space. We have a few properties. One is that it's a linear space. More than that, it has there's natural correspondence between a W and an F. It's a one-to-one correspondence. Okay? Whenever you talk about a function, you're actually talking about a vector. So effectively, you can pick whichever one you want. And typically, you like vectors more better than function because you can think about vectors. Okay? So it's good. Modeling-wise, we think about function, but operational-wise, we talk about vectors. And we know the stuff that we can do about vectors. So we can do linear spaces, but we can also define an inner product on functions. Okay? We can define the inner product on any two functions, f and f prime in H. How? Just because every function is a vector, we know the function of a vector. It's completely trivial now, so we're going to just make this more complicated in a minute. But just appreciate that this is easy now. So let me just call this W transpose W prime, okay? Where W is the vector associated to F, and W prime is the vector associated to W prime. And for those of you who were not around yesterday, we're often going to use this notation for inner product, the pairing notation. Okay, is just a change of notation. I'm going to use it all the time, so get used to it because it's going to be used all the time. And if you want, we got yet another little property. Okay, of course here I'm not even have an inner product, you have norms, distances, and blah, 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 blah. And we can notice another small thing, which is that f of x is equal to wx, and then we can use Cauchy-Schwarz inequality. As I told you, you have two inequalities. I don't know what is the other one, but certainly this is one that you want to know. And this tells you that you have this property, okay? What does it mean? Well, at this point, it's not particularly interesting, but it means that if two vectors are closed, then the function are going to be closed at every point, okay? So it's obvious. At this point of view, it's quite obvious. If the weights are closed, then the two functions are going to be closed at every possible point. Agree? So you go from a notion of vicinity of weight to a notion of vicinity of function at every point. This is going to turn out to be a useful thing. Far so good? All right. This is fantastic because it has all the properties you might need. It's super simple. Notice that is actually something that is still used because whenever you have not so many points, and you actually a lot of descriptors for the points, this might be enough, okay? That's one thing we're going to see a lot. If your number of points, if n is not so large and d is very large, the first thing you try to do is to see if you can stick to the linear model without going up, because it might be already enough. It might be already complicated, and this is something we're going to discuss. But generally speaking, it won't be. You might want to go to something more complicated. So one possibility is to actually introduce the second case, which is the case of finite dictionary. So what is a dictionary? It's just a set of functions, okay? So it's phi I from x to r. I goes from 1 to p. It's just a number, which is finite. It's not an infinity. It's just a finite, a set of functions, okay? This is what we typically call a dictionary. We call it it's something that, a lot of time you can think of it, what is the classical example? The classical example is that if you have some space and you can define a base of the space, okay, in some precise sense. And the dictionary is just a general term that defines bases and things that are more general than bases. We'll see in a minute there are more general notions. So it's just a collection of functions. The elements of this dictionary also have some names attached to them. They're called either atoms or features. Atoms, I don't know where it comes from, but it's the classical name in harmonic analysis and signal processing. Feature is kind of a machine learning thing, and it's kind of a cute point of view. It's basically saying, look, this is a function that takes the input and generates numbers. So you can think of descriptors of the inputs. So if the input is an image, okay, when I build the phi1x, I'm picking a feature, a number associated to the image. Phi2x is another number, and so on and so forth. These are descriptors, numbers that describe the input, and we can think of them as features. These are just names and interpretation, but this is all they are, okay? What is the idea? The idea now is that we want to build the space of function h, is the space of function from x to r, such that W in Rp, f of x, f equals sum Wj, phi j, j from 1 to p. Okay? So linear combinations not of the original features, but of the original coordinates of these features. Do I need to consider that the restriction that x is Rd? Really, it's all hidden in these guys. I don't even tell you what these guys are, but they can be whatever, right? Suppose that this is the space of possible graphs, and George tells you that he has 10 functions that are amazing to describe graphs. All right, they are your functions, and that's it. So x can be whatever, okay? And of course, here we're a lot of information on how we choose them. Clearly, there's going to be a ton of prior information on how you design this. And that's not what we want to discuss right now. We just want to suppose that somebody give it to you. What do you do with them to build functions? Well, you do the obvious thing. You take that thing because you like it, and you just generalize. Okay? You can view this as basically some preprocessing of the data, and then you use linear functions, and that's it. Okay? Let's look at the properties of this guy. Is it a linear space? He's looking on the floor, but he's doing this because it is. Okay? What about the second property? Can I define an inner product? Then it's tricky. Yes or no? Yes, but in general it might be complicated. There is one complication. What is it? Look, we're writing this down, right? If these guys are linearly independent, it means what? There is just one way to build this function doing something like this. Okay? And then we do have this. And it's important because then it means that when we write this symbol, we give from there is just one W and one W prime associated to my F. So this first line makes sense because there is just one guy. Okay? Suppose that they're not linearly independent. Then it means that I'm able to write down the function in many possible ways. And so what do I mean? That I take the W corresponding to that. I have many possible Ws. We can actually deal with that case. We're only going to do it. But for now, we just want to make our life easy. And we're going to just assume that this is a dictionary of linearly independent atoms. Okay? An assumption we make for now. Interestingly enough, we will be able to, by introducing reproducing Hilbert space, we will be able to just remove this assumption, and we'll be able to actually remove the assumption that this P is finite. We're going to be able to take infinite dictionaries. But for now, that's what we want to introduce. Richness and redundancy. So the question is, why would you not be happy with this assumption? Because it's a restriction, okay? And when you make a restriction, it means that you're limiting your choice, okay? So suppose, for example, that, in similar process, the classical example, I give you a function that sometimes is very smooth and sometimes has very big spikes. Then which basis do you use? You take something like sine and cosine, they're very smooth. You take spikes, and then there are two. So you say, oh, I'll just put them together. If you take a basis and another basis, then you put two bases together, you don't get a basis anymore, okay? And generally, suppose that you just give you images, and now you invent features, okay? Or text or strings or whatever. Test this. Yeah, you might have correlation. You might have collinearity of some features because you just pulled them out of experience, right? So it might not be easy. So it's both for the ease of design and the richness, and because it's interesting to have rich function spaces. These are typically the reason why it's interesting to go beyond this, okay? Any other questions? So if I don't do it, remind me to repeat questions because these get recorded and you don't have a microphone. So if I don't repeat the question, it will be interesting to watch the video in the future. All right, so don't let me repeat the first two lines. They're the same, okay? Well, I'll repeat them. So this is one-to-one, okay? I can define the inner product just in the same way because this is one-to-one. Again, this is RD, right? Well, I'm not going to repeat it, but this is just, and this is RP. And I also have this property that if I have f of x, doing exactly the same reason before, I'm going to get the norm of W, and then I'm going to get the square root of sum j from 1 to p of phi jx. Okay? The same properties as before. As long as I'm sure that if I have this kind of sum is finite, which is always true if I have a finite number of dictionaries, I still have the same property as before. By looking at the vicinity of the weights, I know that functions are close at every single point. All right? So it's not bad what we have right now because we have spaces that, which you can do a lot of operations. Suppose that I ask you to compute gradients. Well, if you have to minimize this guy, basically it's not a function anymore. It's equivalent to putting a vector. So if you want to try to minimize some stuff, you can just try to do multivariate calculus, and that's it. And because you have an inner product, you have a notion of orthogonality, so you can do many, many different things. Okay? You will basically have linear algebra for And that's what we're shooting for. The fact that we can move from the linear case to this also gives us some freedom, because we can basically build now nonlinear features. These guys don't have to be linear. You can take the first coordinate and square it, take the cosine, take the Gaussian. Of course, you can ask, okay, how do I do it? I don't know. That's a big problem we have to face. But for now, you can just see that you have a lot of flexibility. By basically using the machinery of linear algebra, which is basically what linear functions do, you can actually consider nonlinear models. And notice that there D is the features of the data that I'm assuming to come in a raw format to be really vectorial. Here, P is what? Whatever, okay? Whatever you're choosing it to be. 3 gazillions or 3, it's up to you, okay? So I can have a lot of richness by increasing that. Clearly, I might have at some point some bottleneck from a computational point of view, because something might get big. The number of coefficients gets much larger, okay? But for example, for any number of points, you can choose a number of features which is much larger or much smaller than the number of points. Well, the thing that we would like to achieve a few things here. We would like to see if there is more ways to actually build function spaces, and we would like to kill the one main restriction we've done so far, which is assuming that P is actually finite, is a finite number. Because so far, whenever you chose a P, you fixed a priori a finite number of parameters, and that's it, okay? We would like to see if there is a way to actually allow ourselves to work in larger spaces, okay? Going back to this thing, we want to be able to work on a large H, okay? Very large H. For example, a space H which is infinite dimensional, not just finite. Now, you could say, if you were here yesterday, what I basically discussed, if you have function spaces that are, if you have a linear spaces with inner product, if you want to generalize them to infinite dimension, you have of some technical condition, basically the fact that some converge, that series do converge, series of functions do converge, and then you're good to go. And the name of that we give to a space with this property, which is a linear space plus inner product, completeness, this property that Cauchy sequence converge that ensure that things are in the space, blah, blah, blah. Again, for those of you who were here yesterday, we spent a bunch of time. Other ones, you might want to look at the first line of the definition of what you call a Hilbert space. So that's the most natural thing to do, to say, okay, I want to go to infinite dimensional. I want to keep everything I have there. I just say, okay, give me a Hilbert space, basically a linear space which is infinite dimensional. It's not enough. Okay, turns out that that's not quite enough, because this, you see, I have more there. I have a linear structure that helps me out. In case you have some linear structure. If you just take any generic Hilbert space, you have to sweat a bit more to get some linear structure. It turns out that there is one other assumption that we make, and actually gives us a lot of juice, and it's a bit more technical. So this way introducing these spaces is by far the most general one, and this is the property of having functionals continuous. It's a very abstract requirement. Basically says, suppose that you consider the map that I call EX, that for any H goes into by taking F and just returning F in X. Okay? It's a map that takes a function, evaluates the function at the point. By requiring this map to be continuous, we basically say that for all epsilon bigger than 0, there exists a delta bigger than such that for all x, if f minus f prime is smaller than delta, then f of x minus f prime x is smaller than epsilon. Okay? I write here already f of x rather than f prime, but this is just the evaluation function, okay? It just says this map is continuous. This is not the friendliest thing you might think of, but you see here that it's just that we go this way just to appreciate the fact that there is this kind of a very axiomatic way to get to some spaces. We're going to spend basically from this moment on, try to see how we can make this thing practical. Okay, so it's intentionally brutally unpractical just to appreciate how little is the story when you take an axiom. point of view. It's just a Hilbert space with one extra condition that seems innocuous, seems somewhat technical. It turns out to actually gives us a lot of things for free, essentially. So let's just convince ourselves that that actually is not such a. We're going to see that what are all the consequences of this assumption. Let's just illustrate how this assumption is not trivial. Consider two basic function spaces. Yeah. What, sorry? Yeah, sorry. H is a Hilbert space of functions from X to R. Okay. So Hilbert space of functions X to R. Okay. Sorry. Okay. Okay. So let's just, rather than keep on staring at this, which is really not that informative for now, let's just check why it's not a trivial requirement. Consider X to be equal to just, say, 0, 1. And consider H. And let's check if L2X is OK. Let's check if L2, 0, 1 is OK. Is it a Hilbert space? Well, let's check. It's a linear space. I can sum up square integrable functions. Yes. Do I have an inner product? Yes. Is it complete? Yes. Believe me, otherwise check it. Do I have the property that the evaluation functionals are continuous? Notice that a consequence of this is that if f, that you basically have this kind of inequality. That up to a constant, you have that the value of the is exactly what we asked here. Another way of writing this result is basically saying that if just put f prime to be 0. Okay, this means that if f has a small norm, then f of x is a small norm for every value. So in particular, I can rewrite the whole thing in a compact way this way. Okay, so it's exactly this requirement here. Okay, now I actually put it as an assumption, as a request. Is the request. Okay, I'm just asking this to be true. Is this true for L2 functions? What am I asking you? If you take a function in 0, 1 and you take its integral, with that integral, can you control what the function does at every single point? Why? Well, because integrals don't care about single points. You can take any single points and shut it up to infinity. You can take any finite number of points and shut it up to infinity, and you just can do whatever you want. So L2 is not enough. It's too big. Okay? I have too much freedom. So L2 is a space that satisfies this assumption, but not this one. The integral of a function does not control what the function does at every point. Can you think of a function space with a norm that actually controls what the function does at every point? No. Can you think of another function space? Simple, like this, where you have a norm, and that norm controls what the function does at every point. Continuous functions, okay? Just a continuous function. Again, on 0, 1, say, same example. What is the norm? Is exactly the maximum. One classical way to define a norm on this space is to take the maximum Does this control what the function does at every point? Well, yes, you take the worst one. If that goes to 0, everything goes to 0. Agree? Is it a linear space? I take two continuous function, I get a continuous function. An inner product that gives me that? No. Turns out that this is, again, one of the prototype examples of a norm which is not given by an inner product. So I'm, again, violating what's happening here. I got almost all the way down. I got this guy, but I didn't get this guy. So this is just to appreciate how this simple thing rule out the functions that come to your head. Okay, L2 and CX, not okay. Too big, too little. Okay. So this is what we call a reproducing kernel Hilbert space. Should I write it for once? And I typically write shorten it as RKHS. And again, this definition is on purposely abstract, just to see how somewhat general it is. One problem is that it's pretty useless. And it actually doesn't explain why we call this guy reproducing kernel Hilbert space. Okay, Hilbert space, yes, but why reproducing kernel? Unclear, okay? Well, it turns out that whenever you have this assumption, you actually get one special function for free, which is going to be useful. And it's what we call a reproducing kernel. So we're going to now introduce the function and show that it comes for free and is equivalent to having a function space like that. So we define a reproducing kernel as so it's a function k that goes from the input to the reals, and it has two properties. If I now fix one entry, okay, so you take kx and you leave the other entry free. This is a function of one variable now. I fixed x, and I leave the other one free. So this function has to belong, reproducing kernel of Hilbert space of functions h. Okay, so I'm assuming that I have a function space, and I say that this function space has a reproducing kernel if there is a function like this with two properties. If I fix one entry, the function that I obtain belongs to the space. Okay? And if I take the inner product of any function in the space with this function here, then this gives me f of x. Okay? Again, it's an abstract definition. I basically say, that the Hilbert space has a reproducing kernel if in that space there is a special function with two properties. Fix an entry, you get the function in the space. Take the product with that function you obtain by fixing an entry and multiply by any other function, you're evaluating that other function at the point. Okay? The whole story is going to be abstract for a little more, okay? And then we'll see that it gets more and more constructive. For now, it's going to be mostly structural assumptions. Now, basically, it turns out that the assumption of evaluation functional be continuous or the existence of a reproducing kernel are equivalent. So whenever you make this assumption, it means that you have this special function. Whenever you assume that you have this special function, you actually have this second property. These two things are completely equivalent. The first, I don't need to discuss because it's the same in both cases. Okay? Which one do you want? So if you're suffering, it's okay. That's kind of the moment where we try to make you suffer the most so that you go away. We have more seats and less p sets to correct. But this moment is designed on purpose. Okay, so it is cannot be much worse than this in this course. It's not going to be any worse than this in this course. All right. So just because I always forget the names. I don't remember the names, but let's just write what I just told you, okay? Let's see. This is the only one I cannot pull up. All right, so just remember, RKHS is this definition. That guy is a reproducer, okay? So there is a theorem that is easy to prove in both directions, but one is trivial. The other one uses super deeper result. If H is RKHS, then kernel. Okay, let me just shorten it, otherwise to write 15 times. It's just what I told you. Basically, if I have a Hilbert space with continuous evaluation functional, then in that space there is a special function like this, and there is only one. Okay? If H has a reproducing kernel, if I give you a Hilbert space with one of those special functions, then exists a unique RKHS. This is slightly, the exist unique symbol is just for my laziness, but it's for there exists a unique reproducing kernel associated to RKHS. Given a Hilbert space with an RKHS, there exists with a reproducing kernel, there is only a unique reproducing kernel Hilbert space associated to it. Okay? Yes. Yes, but to be this guy, it has two properties, right? So let's say. Okay, just clarifies. So H is a Hilbert space. I don't tell you anything about the evaluation functional, but I tell you that it does have a reproducing kernel. Then it is a reproducing kernel Hilbert space, which means that it also has the second property. If I give you a Hilbert space that is also the evaluation functionals, then there exists inside only one reproducing kernel. Okay? They're the same. They're the same. Okay, if you want it, then. Good. We're getting to the correct statement. Converging, just 2 steps, hopefully. Okay. I don't want to do the proof. It's literally 2 lines. Okay. The direction. So B is elementary, meaning that you use nothing. You literally write down the definition of reproducing kernel. It's actually kind of obvious. Look, I wrote it here. Okay. What do I need to show? I need to show that this guy is continuous. Okay. Well, but if I have a reproducing kernel, then it means that the evaluation functional can be written this way by assumption, because that's what a reproducing kernel is, right? And then I have to show that this norm controls this at every point. So let me put, how do we do it? How do I control that the norm of this controls that? Well, nothing, I just take Cauchy-Schwarz. I divide this and I say that this is smaller than norm of f, norms of kx. Now, norm of kx might be big, but it's finite, because by assumption, kx belongs to the space. So it means that the norm of f controls f of x. This is exactly what I need. So in this sense, it's elementary. This is the whole story. Okay. So all you needed to do is to use the definition of reproducing kernel and Cauchy-Schwarz and look at it. This is the kind of proof that we do in this course. Say it again. Yeah, if I put it here. Yeah, so in this definition, I think that strictly speaking, I'm doing this, okay? You're correct. I think this is what I want. Okay, yeah. Of this line? The continuity, so this is just, this is equal to EXF, EX prime F, you agree? So it means that this line is just the continuity of this functional. It says that this functional is continuous. If you give me closed inputs, the outputs of this function are closed. Is that enough? Yeah. Yes. It's like the yeah, I mean, it's just what happened. If you otherwise, it's outside. It's basically it. You call a square interval function is a function for which the norm is finite. Okay. So the two questions were what was how to what question is just the continuity. I skipped this one line because it's written here. The question is every function in a Hilbert space has finite norm. Yes, and that's what I'm using there. Okay. The other direction, A, is not elementary. Use what is called dilemma. This is actually a deep result, and we're going to skip it for now. Okay? We're going to skip it because it is because it will just stare me with even more confused eyes. And we're gonna maybe do it in the next class. Okay? It doesn't really matter for now. It's just a technical thing. What I want to do now is actually show you some examples instead, okay? So that we don't leave with just what the hell we've been talking about for an hour. Linear spaces and then what the hell for like an hour. Okay, let's start to do an example and then we can do this, okay? It's short, it's not it's short, it's one line too, it's just that it's like puzzling because you use a complicated result. Well, I introduced this because it also makes it a bit easier to check the fact that the space we're dealing with is a reproducing kernel Hilbert space. We basically have to check, because you see clearly that once I have this theorem, if I have this theorem, I can also give a definition of two of reproducing kernel Hilbert spaces, which is what? I said, if I have this theorem, I can say that something is a reproducing kernel Hilbert space if is a Hilbert space of functions, and B, it has a reproducing kernel. Okay? I basically can trade the evaluation function with reproducing kernel. And I gain a bit of substance, right? The evaluation functions are super up. Kernels are something that I can start to touch. All right, some examples. Is this a reproducing kernel? Hilbert space. And if it is, what is the kernel? Well, I claim that this is a reproducing kernel Hilbert space. I mean, it's clearly a Hilbert space. It's linear, it has an inner product, I define it, it's all good. I just have to check that it has a reproducing kernel, and I claim that the reproducing kernel is this guy. How do you do it? How do we prove that this is true? Well, we have to check two properties. This is not the best use of the board that I could have done. We have to check that, if we erase one entry, it is a function in that space. And then I can write f of x as the inner product of f times that one function. All right? Let's try to do it. Where? Here. So first of all, let's delete one entry and check if it's still a function. Is it a function in the space or not? Yeah, these are just a bunch of numbers. These are the functions. I'm doing a linear combination, so this thing does belong to H. Agree? That's it. Give me another function, f. Generic function. How is it defined? Like this. How is the inner product between f and kx defined? How is it defined? You remember? Take the two functions. Now there is a one-to-one correspondence between the function and the coefficients. So what you do, you just take inner product of the coefficients. Okay? So the coefficients of the second function, so of the first function, are the wj. What are the coefficients of the second functions? phi jx. What is this? F of x. Okay? So whenever you're dealing with a finite dictionary, which is made of linear independent elements, is a reproducing kernel Hilbert space, and the kernel is this guy. Okay? We see that actually you can go the other way around. Anytime you have there will be a correspondence between kernel and things like this. What if my function, if I consider the special case, so consider the special case where phi j is just equal to xj. Okay, so sorry, phi jx is equal to xj. Then it's just the linear functions. And then I just get what is called the linear kernel. So it's the case where the inner product is just the inner product of any two vectors. Okay? So this is a reproducing kernel Hilbert space with kernel given by this. This is a reproducing kernel Hilbert space with kernel given by just the inner product. Okay? Let me give you one more example that we're going to discuss next time. So I just told you that L2 is not okay. Can we make L2 okay? So consider H to be a subset of L2. And again, let's just do L2, 0, 1, okay? No, let's do L1. Yeah. Just one dimension, though. So, and let's consider the space of function H such that when you consider the Fourier transform, some finite gamma, okay? Again, I'm assuming that you know what is the definition of Fourier transform and not much more. So you have time, then you go to space. You can think, sorry, you have space or time you want to call it. You go in the frequency domain, which is the omega space, and you can think of those as some kind of description in terms of harmonics and sine and cosine, blah, 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 blah. Okay, I'm assuming that I'm not talking stuff that you have never seen before. Otherwise, Tommy would tell you to just go away. Clearly, this is not, sorry, this is an omega, okay? So this is basically saying, if I look at function in L2, I'm not considering any function. I take, first of all, the function for which I can define the Fourier transform, but then I don't take all possible functions. I take the one which in the Fourier domain, they are only supported somewhere, okay? If you want, if you interpret this omega as frequencies, it means that I don't have all possible frequencies. I have frequencies up to a maximum frequency, and then I have nothing. Of course, this is not all possible functions, right? These are not all possible functions. It's not even all possible square integrable functions. It's just some functions. Let me define, you can check easily that it is a subspace of L2. So it is in a linear space. And you can define the inner product of any two functions to be just the inner product in L2. Well, it turns out that this is actually a reproducing kernel Hilbert space. The kernel the sink. Okay? So this is the first example. So Fourier, so this is the first example. It's called translation invariant kernel. They're called translation invariant because actually they don't depend on x and x prime, but only on the difference between x and x prime. And there is a whole series of kernels we can define this way: the Gaussian kernel, the exponential, multi-quadrix kernel, and so on and so forth. They're actually kind of an interesting class of kernels, and they start to show some insight, which is that reproducing kernel space are large but not huge. They just cover functions that have to be simple in some sense. Here, for example, we see that they're simple because they don't have arbitrary frequencies. They have frequency only up to a given prescribed maximum value. Think 1 second how you would prove this, okay? The proof of this is actually not too long. You basically have to use the property. Realize that whenever you write a function, here is not, you can norm in frequency, and you're just sitting on an interval, not on the whole thing. Then you use the inverse Fourier transform, and remember that if you have an interval, the interval and the sink, they're somewhat related by Fourier analysis, okay? That's all. These are, let's stop here. So we start from simple spaces. We actually went to crazy spaces. We're trying to go back to stuff that we can use. We went to crazy spaces to show that they're general. Now we look at linear space. We really recover what we did before, and now we're going to take a step further, okay?